Hi, so we've got this is question 6 for the Unit 2 worksheet, worksheet 2, and the question reads, an athlete trains by dragging a heavy load across a rough horizontal surface. The athlete exerts a force of magnitude F on a load at an angle of 25 degrees to the horizontal. Once the load is moving at a steady speed, the average horizontal frictional force is 470. Now, what is the steady speed telling us? Well, that the acceleration is equal to 0. So the force net, the net force, when we add up all the forces acting on this, is equal to 0 newtons. So what's happening here is you've got this force there of 470 in that direction. You must be pulling there with a force also of 470 to balance that out, and then you've got this vertical force here. Can't see it because I've been drawing through the picture here, but that has been balanced out by the actual weight. So that force is just balancing out that weight, so it's actually making it a little bit lighter, but there is no net force acting. So calculate the average force F that will enable the load to move. So we're looking at this. So we're actually looking at this value of F. So it's just a bit of simple trigonometry here. We've got this triangle here, a right angle triangle. With this is 470. This is 25. We're looking for this. So we're going to get the sine of, no, sorry, not the sine. The cos of 25 is equal to 470 divided by x, and so that force, which is the x, we would calculate as 470 divided by the cos of theta. So let's just do that. 470 divided by the cos of 25, and it gives us a value of about 474 newtons. But because all of these values, as you can see, are two significant digits, we would write this to two significant digits, so this would be 470 newtons. Then it says the load is moved on a horizontal distance of 2.5 kilometers. Remember to change that into meters, 2,500 meters, for 1.2 hours. Remember to change that into seconds by multiplying by 60 and multiplying by 60 again. The work done, so the work done would equal the force times the distance. Now it's in the direction of the motion, so the 470 is in the direction of the motion times your 2,500, and that will give you a value 470 times 2,500. We get a value of about 1,175,000 joules, but again we put that into two significant figures, so it will be 1,2,0,0,0,0, 1.2 megajoules, or 1,200,000 joules. The minimum average power, well, the power is equal to work over time, so it's going to be that 1, 2, and all of these zeros, divided by the time. Now the time is going to be 1.2 times 60 times 60, so we divide by 1.2 times 60. Remember to use your brackets when doing this, so that you do a correct division, and that equals to be about 271 watts, but we will put that into, again, two significant figures, 270 watts. Finally, the question is, the athlete pulls the load uphill at the same speed. Explain in terms of energy changes why the minimum average power required is greater than in B2. Well, the athlete still has to provide a force to overcome or to do work to overcome the frictional force. So to work to overcome the frictional force stays the same. Force is the same. But now also has to provide for greater potential energy, because the ball actually gains height, so it's greater PE, potential energy. So that needs work to be done on that to raise. It has to raise the load vertically. So that's going to require extra work, so greater power if it's going to be done at the same speed. See, same speed, therefore the same time, therefore greater power is going to be required. Okay, so that was that question. Question number 6. Thank you very much.